Sorry for this technical problem, but we are ready to start. Thank you.
Thank you. Okay, let me start. I start with introduction. So first, I give some backgrounds of our study. In 2022, several attacks on SIDH using founded by these papers. So in the following year, and that uses the SIDH tag technique for decryption. And this PKE seems to be resistant against the SIDH tag. However, it requires high degree isogeny computations, such as 3,779 isogeny. So the computational cost is relatively high. So here are our contributions. First, we made a new algorithm called random isogeny images that computes a random non-smooth degree isogeny using SIDH tag and quaternion algebra. And using our new algorithm, we made a new key encapsulation mechanism named QFASTA that is based on FASTA. And our QFASTA has significantly smaller data sizes of public key and ciphertext than FASTA, and it only requires 2 isogeny and 3 isogeny computations, promising a reduction in computational cost. In addition, we proved that QFASTA is INDC secure under some assumptions. Next, preliminaries. So here are some notation. First, lambda is and M sub n is a set of invertible diagonal matrices of this form. And B sub SF is a separate part of an integer C. For example, 50 equals 3 times 3 squared times 5 cubed. Then B sub SF equals 3 times 3 times 5. And B sub T infinity is the quaternion algebra defined by these relations. So please note here that this squared is minus 6, not minus 1. And n alpha is the reduced norm of a quaternion alpha. And finally, the elliptic curve, the E and C curve something represents super singular elliptic curve over the field of this curve. Okay, so next I explain the Boolean transform. So before the statement, let me introduce the definition of order. This is the definition. An order O is a coupling of the quaternion algebra B, represented by this form, where alpha 1 to alpha 4 is a basis of the quaternion C. In addition, an order B, order O is said to be maximum if there is no larger order that contains O. Then the Boolean correspondence gives us the isomorphic between the n-morphic rings of the curve E and maximal order O of the quaternion algebra. In addition, it is known that the degree of an n-morphic alpha is equal to the norm of the corresponding quaternion. So here is an important example. So let's zero the curve of this form. Then the n-morphic ring of E0 is isomorphic to this maximum. And in addition, the map eta corresponds to the element I, and this Frobenius map. The Frobenius map corresponds to J. From now on, I denote these curves by so next, I explain an important algorithm, the name that is based on drawing formula. So it takes an integer m rather than the prime t, and it outputs for tangent gamma in O0, I find that gamma is in M. So from the drawing correspondence, the output gamma can be seen as an endomorphism of the part A0 whose degree is M. So I mean this algorithm outputs the endomorphism of A0 over a fixed degree. Next, I explain how to compute one-dimensional isogeny using two-dimensional. So that is the technique using this idea. So I use this diagram where phi1 is an isogeny of degree 1, a degree E1, and psi2 is a degree E2. And F is the composition of psi2 and psi1 f. And B equals B1 plus B2, and P1 P1 is the basis of B Poisson algorithm. And finally, okay, so under this equation, it is known that if we're given these fixed values, P1 and P2, then we can compute P and psi1 and psi2 by computing DB isogeny. And especially when the D equals 2 to the 8, then DB isogeny is just a chain of 2 to isogeny. So it is easily computed. So in this talk, we denote this algorithm by finite evaluation. Okay. So next, I explain FESTA. So here is the FESTA system parameter. This is normally contained. I find these three conditions. And positive conditions is necessary to compute all isogenies for degree B1, B2, B1, and B2. This is because we have to use theory form. And the third condition is to execute some acceleration system. And in addition, 0Q0 is a basis of 2 to the B torsion subgroup. First, compute a random B1 isogeny from A0 like this. And then compute a random B2 isogeny like this. And next, take the random matrix A and let RA and SA be A times phi to 0 and phi to 0, where phi is the composition of phi1 and phi2. Then, the public key is EA, RA, and SA. The secret key is the matrix A. Next, coding is like this. But convert the message M into the B1 isogeny and B2 isogeny and a random matrix B. And then compute R1 S1 and R0 S2 like this. So the hypothesis is B1 R1 S1 and E1. So finally the coding. So we first define psi1 and psi2 like this. So in this diagram, psi1 is essentially this one. 1, 2, and psi2 is this one. And let B1 be the degree of psi1 and B2 be the degree of psi2. Then B1 plus B2 equals 2 to the B from the third condition of the system parameter. So we now we want to compute this psi1 and psi2 by using finite evaluation. So here we go, we need to compute R2 prime and S prime. That is the images of R1 and S1 under the support diagram. And this point can be easily computed by using the secret matrix A here. And finally, using standing evaluation algorithm, we obtain psi1 and psi2. And using this psi1 and psi2, we compute phi1, phi2, and b, and convert phi1, phi2, b into matrix M. Okay. So here are the concrete parameters for test. As you can see, we need to compute very high degree accuracy, such as 2061, 2700. In addition, the tightness P is as large as so. What is test parameter for large? So in my opinion, the reason is that these two conditions are so strong, and especially the smoothness constraints are quite. So to avoid the smoothness constraint, we want to compute the non-smooth degree isogenies without using the formula. So now, first, we made a new algorithm named random isogeny image that computes. So from now on, let's see the assignment before and see the realization steps to the algorithm. Then this algorithm takes as input an S integer b smaller than to the a and finally factor s. This output the full domain of the random b isogeny type and the
Yeah, I'm gonna zoom here.
Um, yeah. Okay. We are ready to start our second paper of this session. It's going to be radical squared and balloon isogeny formula by Thomas Tomateclu. Thomas, please. Go ahead.
Thank you. Even though this is the isogeny track, I will not make any assumptions. Maybe you dislike the other tracks more, or maybe you got lost here on the way to the beach. So one slide to talk about what isogenies are. Isogenies are maps between elliptic curves. We're going to stay in dimension 1, unlike most of the other talks. And you can see these maps are basically pointwise maps. These maps have a lot of nice properties, as you probably know, otherwise the field would not exist. We will need very few of these properties. The most important one is going to be the degree of an isogeny. In this case, it's rather obvious. This point on the codomain curve has 3 pre-images, so the degree will be 3, because every point will have 3 images on the codomain curve, right? And they're maps, so we can also compose maps, of course, which is very typical. Let's say we have another codomain curve and we map these 2 points to this one point, and this will be an isogeny of degree 2. And we'll call that a 2 isogeny. And then this composition will, of course, will be able to say that this is a 6 isogeny. Why? Because the degree will be 6, because this point on the final curve will have 6 pre-images on the first curve. That's pretty much all you need to know. We can abbreviate it like this. We will ignore the pointwise evaluation. Maybe one extra thing is that we can also ignore the arrows on the maps. We can just remove them. Why? Because every isogeny of a particular degree also has a dual isogeny. If you're not too familiar with isogenies, it's similar to an inverse. It's not really an inverse, but feel free to think of it as an inverse. Okay. Now, the radical isogeny formulas are mostly applicable to C-side. So I'll give a very brief sketch of C-side on a toy example. We're going to be working over the field F647. It's a prime field. We're going to work with a subset of all elliptic curves over this prime field, namely the supersingular elliptic curves with a specific endomorphism ring. If you don't know what that means, that's fine. Just we have 23 of them, right? And the point is now all these nodes represent one supersingular elliptic curve, and we sort of want to hash into that in the sense that we want to start from one curve and then move around this graph as quickly as possible using isogenies. Now, there's a reason why I've drawn them in some sort of circle, because let's say we also display the 3 isogenies as some edges between these nodes, then it looks like this. Every supersingular elliptic curve in this setting has 2 outgoing 3 isogenies, and they form one big cycle. Now, in this toy example, it's pretty fine, right? I mean, going from an elliptic curve at the top, for example, it only takes 11 3 isogenies to go to even the ones at the bottom. But for cryptographic purposes, we're working with roughly 2 to the 256 of these nodes. So we would require an exponential amount of 3 isogenies to compute this. So the solution to this is to add more prime degree isogenies, namely 5 isogenies. It may not be noticeable, but this is also a cycle. They're not disjoint cycles. You can just move around them as well. And you can add as many prime degree isogenies as you want. If you use, in this toy example, 3, 5, or 7 isogenies, I think with 4 isogenies at most, like just take a 3 isogeny, a 5 isogeny, and 2 7 isogenies or something, you can move from any node in this graph to any other node and move around quickly. So for realistic parameters, we have 512-bit prime P, which is constructed in a specific way to easily be able to compute that. We have 73 primes and then another prime 587 to make this P prime as well. And for each of these 74 primes, we will compute at most 5 isogenies of that degree. Why 5? By 5, I mean we go 5 to the right, 5 to the left, even though left and right don't really have a meaning here, but whatever. But we can also do nothing, right? So for every prime degree isogeny, there's 11 options. At most 5 to the left, most 5 to the right, or doing nothing. There's 74 primes. So 11 to the 74 is roughly 2 to the 256. And in this setting, we also have 2 to the 56 elliptic curves. So we sort of expect to reach all of them. It's not exact, but it's close enough. So the main topic of this talk will be, how do we actually compute these isogenies? Because in general, isogeny-based cryptography is a bit slow. And computing isogenies of degree 587 is already sort of, well, sketchy is not maybe the word, because in the previous talk, we saw isogeny of degree 3000, etc. But it's already useful to start thinking about optimizing this. Maybe some people are familiar with this. These are the classical value formulas. We don't really need to memorize these formulas or even understand them. This is from the 70s. At the top in the teal, you see the starting curve in long Weierstrass form. At the bottom, you see the codomain curve. And in between, in orange, the most important part is highlighted. Why? Because we sum over some subset, and the subset is linear in the degree of the isogeny. In this case, we denote it by n. The fact that it's linear is important. There's some tricks to do it like an n over 2 or something. If you have an odd degree isogeny, for example, but regardless of the formulas, the amount of multiplications or work in general you have to do is linear. You can do it on other curves as well. Edward curves. This is, for example, Montgomery curves. You have a domain and a codomain curve. But here as well, you sum or you do a product over some sort of subset. And again, it's linear in the degree of the isogeny. And this is also how the original Seaside implementation worked. Essentially, for all 74 primes, they just used a value formula. I think on Edwards curves, but I'm not 100% sure about that. But that was in 2018, and this is how they implemented it. This is kind of tricky. Why? Because for every of these isogenies, you sort of need to sample torsion points, which is very expensive because typically you want to do that, or you have to do that by using full scalar multiplications of an elliptic curve. There's some trade-offs to be had there. I'm not going to go into depth about that. Essentially, if you want to compute a 15 isogeny, you can 3 isogeny followed by a 5 isogeny. You can use a 15 torsion point, for example. So you can sort of, there's a trade-off, but you then have to do extra work by pushing these points through. But still, it's not really ideal in terms of efficiency. Then in, I think, 2020, there was a sort of big breakthrough in this with the value square root formula, in the sense that asymptotically, we don't need to do a linear amount of work in the degree of the isogeny, apparently. We can do a square root. The amount of work we do is square root in the degree of the isogeny. Also not going to go into depth, but essentially you do like a baby step, giant step sort of thing, and then you combine it with some resultant computation. And asymptotically, it's a lot better than regular value on any sort of elliptic curve form that you want. Asymptotically is obviously not the same as in practice. For Seaside 512, it started outperforming at around primes around roughly 100, depending on the programming language and some other optimizations. Maybe it's like even lower now, 90-ish or 80-ish. But Seaside 512 was then split up into 2 pieces, a regular value formula chunk and a square root value formula chunk. On the other end of the spectrum, you may wonder why we skipped 2 isogenies, why we just went to 3 isogeny immediately, because 2 is a very annoying prime, basically. But you can still compute 2 isogenies, and these are formulas to compute a 2 isogeny. And as you can see, they're rather simple, right? We start from a curve. This is the codomain curve. And on this starting curve, 0, 0 is a 2 torsion point, and the same is true for the codomain curve. What does this mean? If we just reiterate this formula, mapping A to A prime, we essentially keep computing 2 isogenies. So if you want to compute an isogeny of degree 2 to the 1000, you just have to reiterate this formula 1,000 times. That's it. You don't have to sample torsion points, which is kind of pretty cool. Why? Because sampling a torsion point requires roughly 11 log p multiplications on the Montgomery ladder, whereas the dominating cost in this computation is a square root or a radical, which you can do over a finite field by simply doing one full exponentiation. And if you use square and multiply, this is only roughly 1.5 log p multiplications, so it's a lot faster. After that, around the same time as the Villiers square root formula, for example, 2020, we started looking at like, okay, but this works for 2 isogenies, why wouldn't this work for larger degree isogenies? And it's true, this also works for 3 isogenies. You can see, starting from curve, 0, 0 is a 3 torsion point, codomain curve is the same form, 0, 0 is again a 3 torsion point, so you can iterate that again and again. What's the difference? We don't have to draw a square root, we have to draw a cubic root. That's it. But over a finite field, that doesn't matter. Why? It's just an exponentiation. The same is true for 4 isogenies, but that's just two isogenies combined. So, but the same is true for 5 isogenies as well. Formulas exist. We have a domain curve, codomain curve. This time we do some arithmetic, and we have to draw a 5th root. Again, this is just an exponentiation. And this is from 2022. There was some follow-up work as well. We can keep doing that. The problem seems to be that the higher the degree or isogeny, the more extra work we have to do. This E stands for the exponentiation, so drawing the radical, which is a fixed cost. It's always one radical that you have to draw. But the amount of multiplications really grows a lot. The 329, for example, is already a lot of multiplications. And starting from prime L being 23, there was no use anymore to try to implement this in C side because it wouldn't speed it up anymore. But there, the amount of the isogenies in C side 512 were then split up in 3 cases. We have radical isogenies for the smallest primes, regular value for the mid primed, and value square root for the largest primes. Oh, if you've been paying attention, the 587 changed in 409. Why? Because if we want to add 2 as a prime, it's very annoying. You sort of have to change the mathematical setting a little bit, but it's still 74 alt primes and then 2 75th prime. So that's just a detail. So the main question is how does this scale? Can we like expand upon this? Can we do better? It seems to be yes, we can. In the paper, I split the radical Filou formulas into 2 parts. In the previous works, every time we did it, we started from like some curve in some form, EBC, and immediately we tried to go to some curve EP prime, C prime. Why? Because that's the formula we want to iterate, right? It's just that they're very inefficient if you try to do them ad hoc, or if you try to, because all of these were just found ad hoc in some symbolic computation. However, if you split them like this, you actually can find a lot more efficient formula. Namely, the first one is just the classical Filou formula, which we know is linear, and the degree of the isogeny. And then there's an isomorphism to put them back into the same form that we want to iterate these formulas. I'm going to show the formulas for this isomorphism. You can ignore most of it. But again, I've highlighted the important parts. We have this the magenta is just your exponentiation, which is fixed. It's just drawing a radical, which is one exponentiation over a finite field. And all the other parts in orange are linear in the degree of the isogeny. So since the classical Filou formulas were linear, apparently this operation count should be linear on the amount of multiplications as well. And this is the case. This is one of the propositions out of my paper, that we can actually compute an isogeny of degree n to the k. And this complexity 2 log q plus linear amount in n time k basic operations. Remark that 2 log q is basically an upper bound for like the square and multiply. Typically, in general, it's 1.5 times log q. That doesn't matter. A more problematic part is that the hidden constant is 16, which is kind of high. But it's still worth it. So now in practice for Seaside 512, we have this. For all the primes up until 199, we use radical Filou isogeny formula. And then starting at 211, we use the square root ones. This speeds up considerably compared to the previous limited use of radicals. We have a 35% speed up. And in general, compared to using no radicals, it's 64%. The cool thing is that this also scales. Why is it cool? Because the previous radical isogeny formulas only worked until L19. But for larger parameters, these had less of an impact because you only use it for like 11 small primes, whereas for larger parameters, you need more than 75 primes. You need 200 primes or something. So they had less impact. So the 64% is seemingly stable for any larger parameters as well. This does leave some open research questions. The formulas so far are only conjectured. In the paper, there's some attempts at proving it, but I did not find a conclusive proof. Formulas also only work for case n is odd. That's fine for cryptography because even degree isogenies are typically split up into isogenies of degree 2 anyway, and we have formulas for that. As I said before, we have like this constant of 16, which is less than optimal. I think we can do better, so we want more efficient formulas. And we also should probably look at some constant time version of this. Unfortunately, these radical isogeny formulas are not compatible with other attempts at making Seaside constant time. Why? Because you have to compute the same degree isogenies successively, whereas for Filou square root, you sort of can do them simultaneously. So that's also still an open research question. Papers on ePrint, of course. If you're too lazy to type the number, you can scan the QR code. And if you want to contact me with questions or suggestions, this is my email. Thank you.
Thank you. Yes, please. We have a question here.
Can you comment a little bit on the difficulty of proving the correctness of these formulas? Because it seems almost incredible to me that with isogenies, everything is algebraic, right? It should be just polynomials. So why are we having difficulty proving the correctness of these formulas?
So in the paper, like essentially, the straightforward way to prove this would probably be to express your new torsion point in terms of this. Problem is you start having denominators with large summations, which are very hard to evaluate. And then you have to plug them into some n division polynomial, which again is a summation. So just symbolically computing that seems to be hard. Another attempt is something that Damien Robert talked to me about it, where he had some ideas to do some descent, but he didn't quite figure out how this would combine with my idea because his formulas depend on whether n is a sum of two squares or not, which this is not the case at all. So he said like, well, whatever I will end up with, it's going to be different. So it will be different formulas probably. There are some other parameters as well. I mean, so a Weierstrass isomorphism is like a 4-tuple. Two of them are the U and S parameters here. If you can find T as a parameter as closed form expression, it's probably easier to prove it, but even then, I don't know. It just seems very hard.
Thank you. Just a quick question, Thomas. This applies to C-tight, do you think?
Well, that's the thing. C tide is constant time, but that really uses Filou and Filou square root. But the constant time, the practical version of the constant time does not apply to radical formulas because you have to iterate the same degree over and over. So that's still an open question. Yeah.
Thank you very much. Let's thanks the speaker again. And we are ready for our third talk. Yeah. So we will, this third paper is about cycles of pairing-friendly abelian varieties, and it will be presented by Craig Costello. Craig, please, go ahead.
Thank you. So yeah, this is joint work with Maria Cortariel Santos from University College London and Michael Narig from Microsoft Research, who's sitting up there. So the part of the talk that you're going to get really shortchanged on is why we're doing any of this in the first place. So there's a bunch of other tracks here, a bunch of other sessions, sorry, that are talking about zero knowledge proofs, ZK snarks, and proof systems. The good news is, as always, the best way to do these things is using elliptic curves. And so you don't need pairing friendly cycles to do these proof systems. You can just use any old elliptic curve, or not any old elliptic curve, but an elliptic curve of a certain group order. So if you want to prove something about an arithmetic circuit over FQ, you can use an elliptic curve over FP to describe a proof system over that circuit. If you want to prove something, the verification of that proof system happens modulo P. So the circuit that you're proving things about is modulo Q, but the verification algorithm runs modulo P. If you want to prove something about that proof, if you want to layer these proofs recursively on top of one another, you're going to need another elliptic curve whose group order is P. And so you could keep developing a chain of these elliptic curves whose group orders match the previous one's field. But the most elegant way to do that, to have an infinite recursion, is to have a cycle of elliptic curves. So we use this symbol in the middle to denote a cycle. But here we've got the kind of most elegant, simple way to do things, which is an elliptic curve over FP with group order Q, and another elliptic curve over FQ with group order P. If you want your proof system to be succinct, that's what the S in SNARK stands for, you can use a pairing-based proof system. So not only do we have these elliptic curves now over FP and FQ that have each other's characteristic as their group orders, but we've got these extension fields that we have to work over because we're doing pairings now. So this is kind of like a general look at what a pairing-friendly cycle looks like. We've got these two elliptic curves down here, and we've got these extension fields of degree M and N. And this was proposed by Ben Sasson, Chiesa, Tromer, and Verda 10 years ago here at Crypto. This was this really promising way to do scalable proof systems where you can keep recursively layering proofs on top of each other. And the pairing is what gives you these Groth-style proof systems that have very succinct proofs. The proofs end up being just a few group elements in G1 and G2, depending on which curve you stop on. So that's the setup, and that's basically what we're looking at today. Now the cycle that was used in that original paper is the MNT cycle. So in the MNT cycle, the pairing that works over E over FP maps into an extension field of degree 4, and the pairing that takes place over E prime over FQ maps into an extension field of degree 6. So that's the M&T cycle that was used in their paper, where M and N are 4 and 6. The problem with that cycle is performance. So when that was proposed in their paper, I've kind of grayed out some of the other security levels here. I'm only going to talk about the middle one, the one that we all kind of care about the most. But this picture is to try to depict like the suboptimality of that M&T cycle. So over here, we've got a dream cycle, and over there is the M&T reality. So when we're trying to set up these pairing-based systems, we always want to make sure that our elliptic curve discrete logarithm problem is roughly twice the security level. So if we're looking for a 128-bit secure system, we'd like to have a cycle where our elliptic curves are defined over a 256-bit fields. But as these index calculus attacks have got better and better over the years, we've had to keep boosting the size of the extension field that we need to, where the pairing is computed, so that that's got a hard DLP up the top. So if we wanted a dream cycle at the 128-bit security level, maybe 16 is the right number. And ideally, we'd have 2 elliptic curves of prime order down here of over 256-bit fields. And then up here, we've got a degree 16 extension of both elliptic curves to take us to about a 4,000-bit field. We've got 128-bit security there and 128-bit security there, and we're away. Unfortunately, the only cycle that is known, the only elliptic curve cycle that's known, is this M&T cycle. And the M&T cycle, because we're kind of bound by the smaller of the 2 embedding degrees, so we have to make sure that P to the 4 is big enough to reach that around 4,000 bits, which is why we have to choose P and Q to be close to 1,000 bits to reach that DLP security. But in doing that, we've like really overshot the sizes of the elliptic curves that we need to work in. So we'd have to work with elliptic curves over 1,000-bit fields. So like elliptic curves that offer 500 bits of security. That's good, but on the downside, they're going to be really, really bad performance-wise. So this is what we'd love. We'd love a dream cycle like this one, but this is all that we've got, which kind of motivates this work. So a bit more about why these pairing-friendly elliptic curve cycles are elusive. So when these proof system papers came along and used these cycles, they'd already been known for a while. So there was this paper by Carabiner and Teskey at ANTS 2008. And they just pointed out that this cycle exists among M&T curves, kind of just as an interesting thing to point out. It wasn't really considered useful at the time. It's kind of, this was before the proof systems that were looking at doing recursive pairing-based proof systems came along. But basically, since that cycle was observed, there's been no progress in finding other 2 cycles of elliptic curves. There's been a bunch of work motivated by the popularity of proof systems trying to find them. But basically, it's just been a bunch of negative and impossibility results. So there's this paper by Chiesa, Chura, and Widener in 2019, where they looked at a bunch of different ways to maybe try to attack the problem, and ended up giving a bunch of negative results. So negative results along the lines of, you're never ever going to find a cycle where the embedding degrees are 10 and 10 or 12 and 12 or things like that. And then there was a paper here last year by Bella Munoz, Jimenez, and Uros Silva, apologies for the pronunciation, where they basically gave a heap more negative results. So they were looking at a bunch of different embedding degrees, a bunch of different approaches, and kind of ruling out more things that we might try to try to find these cycles. Now, I should say that in fact, the original cycles paper and this CCW19 paper, they explored kind of relaxing the conditions of primality to say, well, we don't actually need both curves to have each other's fields as their group orders, their prime fields as their group orders. It'd be enough if the primes just divided each other's group orders. But if we're talking about elliptic curves over prime fields, then the Hasse interval kind of makes this impossible. It's kind of straightforward to see that the Hasse interval prevents this. The Hasse interval says that P and Q have to be very, very close to each other. They only can differ by like the square roots of each other. So if I let the number of points of this, say, if I write it to be like 2 times Q, and then I come over here and try to define an elliptic curve over FQ that's, you know, that's 1 bit shorter, Q would be 1 bit shorter, then there's no way I can reach a group order of P at all. So that's what I mean by the Hasse interval shackles this possibility. Basically, we're stuck here. And there's nothing, so they prove that we can't have this in general using the Hasse interval. Okay, so that cues what we do in this work. So what we did in this paper was basically we relaxed as much as we possibly could. So we relaxed the fact that A and B need to be elliptic curves. So we said, okay, let's just take them to be, they can be abelian varieties, kind of like the most generalization we can think of any dimension. The second relaxation was that they can be defined over extension fields. And the third relaxation was the one we talked about on the previous slide, that we only need divisibility now. We don't need them to be equal to each other's, the characteristics to be equal to each other's group orders. But all of these relaxations put together allowed us to like really take off the shackles of the Hasse interval and go looking for these things in high dimensions. Okay, so we're not going to see too much of like the technical details. We're just going to see the very high level ideas in terms of the downsides and the upsides. So let's talk about the downsides. Let's try and be transparent about the downsides here, because in a way, like relaxing the dimension and relaxing this condition of the extension fields is definitely kind of cheating. Because so if we look at invoking high dimensional varieties, the reason that they were interesting before, like outside the context of proof systems, just in classical ECC and hyperelliptic curve cryptography, was because as the dimension goes up, we get a lot more group elements. So like, so the number of points on the variety, the size of the group grows exponentially in the dimension of the variety. So what that allows us to do in classical ECC is to potentially exploit the trade-off of reducing the size of the prime P. So a high dimension means a smaller prime P, and maybe that gives a faster hyperelliptic curve crypto system. But in the context of cycles, we're not allowed to shrink P anymore because P is going to be the group order of the other, or a subgroup order of the other thing, and that P needs to be secure against the discrete log problem in the group of order P. So we're kind of lower bounded. We can't shrink P below 256 bits, say at the 128-bit level, because we need it to be secure against pollard row on the other side. So like the whole reason we would have been interested in high dimensions before I guess this work was being able to shrink that P, and we're not allowed to do that here. So it's like already that's not a good sign for us. And even if we have to fix P, we know that the arithmetic grows dramatically. The arithmetic slows drastically as the dimension grows. So as we go up in the dimension, everything gets a lot more complicated and slows down, especially because our primes are kind of staying fixed at a certain size. Another thing we do in this work, it's not inherent in the approach, but it's something we kind of cheated and did, was we set Q to be basically we set Q to be the group order, the full group order of the high dimensional variety over FP to the U. And so it's going to be a high dimensional variety. So Q is going to be a lot bigger than P. Ideally, we'd like Q to divide that group order. and be prime, so it's a lot closer to P, kind of getting that balance. But we cheated our way out of that and set Q to be equal to the group order, which forces the variety over FQ, the B variety in the cycle to have embedding degree 1. And so if you can remember that slide talking about what the optimal situation would be, where they're both kind of as small as possible with the same embedding degree, that really hurts us over on the other side here. Nevertheless, we can still get Q being twice as large as what we would consider optimal. So we're kind of trying to make sure that our DLP securities are at the requisite size and push P and Q down as far as we can go. Hopefully, somewhere between like the MNT cycle and where the dream cycle P and Q could be. So we can still get Q to be twice as large as that by this kind of trick we do in the paper, where we make sure that there's no P torsion to be found until we go up in the extension. But we couldn't do that in conjunction with our best approach on the A side. So we did manage to boost the values of V where we could find P torsion, but we couldn't do these two things at the same time for kind of technical reasons, but also it's not a shut case. It could be possible. We just weren't able to do it. Okay, got all that out of the way. Let's talk about the upsides. So typically when we talk about constructing pairing friendly varieties, even just one of them outside the context of cycles, people explored trying to construct high dimensional pairing friendly varieties before the cycles literature. And they were constructing ordinary high dimensional pairing friendly varieties was very hard. There was work that did it, but they were really suboptimal, kind of bad row values for anyone in the know. So they were even more difficult to construct than the elliptic case. But in the super singular case, it's a lot easier. There's kind of ways where we can write down a super singular high dimensional variety over FP or some extension of FP. And we know it's group order, and we can write down the curve explicitly, so everything's good there, which is good for us, and that's exactly what we do. So in our paper, A is always super singular, and we've got kind of two flavors on the other side where B can be ordinary or super singular. The best one we could find is when they're both super singular. And then we can invoke this theorem from Rubin and Silverberg from almost a quarter century ago, where they say we can start with an elliptic curve over FP to the U, over some extension of FP, a dimension 1 elliptic curve, and we can just consider a subgroup of that elliptic curve over a field extension. So if we're talking about FP to the U, we might consider the group over a bigger extension. And then there's a special subgroup that they look at called the trace zero subgroup of this elliptic curve over the extension. And that allows us to construct an abelian variety of dimension that's exponential in the degree of the extension we take here. So we know that the arithmetic grows drastically as the dimension goes up. The dimension here is growing exponentially in L, but the good thing is that our embedding degree grows exponentially in the dimension. So the hope is here that, yes, we're going to suffer by doing like more complicated arithmetic over extension fields here, but we're getting a boost in the embedding degree. So what that allows us to do is basically get arbitrarily high embedding degrees on this side, on the A side, which especially as the security level goes up, we can get that the optimal size of P on the left-hand side at least at any security level. One thing I should say is that it might already be interesting in the context of like concrete proof systems to look at this construction where P is close to optimal, despite the fact that the cycle on the other, the variety on the other side, this elliptic curve is defined over a much bigger field and is definitely suboptimal on the other side. Oh, we're out of time? Okay, good. That's my final slide anyway. yeah, just, I've got an example there that's kind of illustrating the point on the question slide. This is the 128-bit security level, that's P and Q. And this is one of ours at the 128-bit security level where our P is optimal. And those in the know will know that there might be some interesting things you can already do here with that optimal P. Okay.
One really quick question for Craig. Any question for Craig? How difficult was to find this example, Craig?
This example?
Yeah.
Very easy. It's like, this is the first, this is 2 to the 256 minus 6,000 and something. It's just it's the largest 256-bit prime where P to the 8 minus P to the 4 plus 1 is also prime. So that Q is P to the 8 minus P to the 4 plus 1. And all we're looking for is P where that is also prime and we're away. I think it also, P has to also be 2 mod 3, but that's it. So yeah.
Okay, thank you very much. Let's first speaker again. And we are ready for the last talk of this session. Yeah. So we are, yes, so Mija is going to talk about improved algorithms for finding fixed, finding fixed degree isogenies between supersingular elliptic curves. Mija, please go ahead.
Yeah, thanks. So my name is Mija Stopar, and this talk will be about improved algorithms for finding fixed degree isogenies between supersingular elliptic curves. And this is a joint work with Benjamin Bencina, Peter Kutash, Simon Philippe Merz, Christophe Petit, and Charlotte White-Kemper. So why is it important to study algorithms to find isogenies between curves? Is because most isogeny protocols are based on the problem that it's difficult to find an isogeny between 2 curves or some variant of this problem. So just as a quick illustration, this diagram is about a ski sign signature scheme. And here, the assumption is that if you know if there is a commitment isogeny psi and challenge isogeny phi, then it's difficult to find this isogeny if you don't know the secret isogeny tau. Or another example, which you are most probably familiar with, which is a supersingular elliptic curve version of Diffie-Hellman, where the idea is to use the J invariant of this curve as a shared key, secret key. There are 2 paths to arrive to this curve. And again, the assumption is that, for example, if you don't know FA, you can't get to this curve. But as you know, this is SIDH, this was broken. And it was broken because the assumption was that even if you expose some additional information, even if you expose the images of some points, the problem to find isogeny is still hard, but this turned out to be wrong. There is this remarkable correspondence in isogenies, so which was found by Max Deuring in 1941. And it says that there is a bijection between supersingular elliptic curves and maximal orders in quaternion algebra. So if you take the endomorphism ring of the elliptic curve, you end up with a maximal order. Yeah, for example, if you have a supersingular elliptic curve over some finite field P, then each endomorphism on this curve can be seen as a quaternion element in a quaternion algebra that is ramified at P and infinity. And there's more about this correspondence. So if you have an isogeny phi between two curves, then the corresponding object in the world of quaternions is some left ideal, let's call it I phi, and the norm of this ideal is the same as degree of this isogeny. And this is what we did in our work. We actually moved from the world of curves to the world of quaternions, and we tried to find an ideal of norm D. So perhaps the most important free problems in the isogeny based cryptography are the following. So computing the endomorphism ring of a supersingular elliptic curve, then what was already mentioned before, computing any isogeny between two supersingular elliptic curve, and it was shown that these two problems are equivalent. And the third problem is to compute not any isogeny between two curves, but an isogeny of some particular degree D if it exists. And this is the problem that we addressed in our work. So what are the implications if a better algorithm is found for degree D isogeny? So some schemes are actually based on this third problem. So the security of these schemes is impacted, obviously, and also it might help to improve the performance of some schemes because you are able to compute an isogeny of optimal length. So how did we address the problem? We defined the degree D as P to the 1/2 plus epsilon, and we asked up to what value of epsilon can we compute an isogeny of degree D. And why did we choose such values? It's because there exists an algorithm to compute an isogeny of degree P squared, which exploits the fact that this is usually the shortest isogeny between two curves. And for the degree P to the 3 and more, there is of course KLPT algorithm. P is characteristic of the finite field here. So what was the state of the art before our work? So you could use exhaustive search, which costs O of D. Then there's a meet in the middle attack, which costs O star of squared D. And then there are Van Orscott-Wiener collision search variants, which depend heavily on the available memory. And if we have a quantum computer at our disposal, then there's Grover's algorithm, which improves exhaustive search to O star of squared D. And there's also Tani's algorithm, flow finding algorithm, which is even more efficient, but it has somehow unrealistic memory requirements. So our strategy in 6 steps was the first 2 steps were just to move from the world of curves into the world of quaternions. So in the first step, we compute the endomorphism ring of E1 and E2. So we get maximal orders O1 and O2. And of course, there is no efficient algorithm actually to do this. The best we have is Eisenträger et al. Then the second step was to compute the connecting ideal of these 2 orders. We can do this by Kirchner-Voigt. And then we computed the norm form associated to this connecting ideal I. And in the 4th step, we tried to represent D, or degree D, with this form. So if we get x1, x2, x3, x4, for which this equality holds, then we can use this x to compute an ideal J by using this formula. And this ideal J is equivalent to I, and it has the norm that we want. So it has norm D, and then we can move back to the world of curves. We can translate it to the isogeny of degree D. So what we focused on was the 4th step. So we try to represent D with different algorithms, with Kornakia and Coppersmith, with different versions of Coppersmith. So Kornakia is an algorithm for solving the equations of this form where delta and m are co-prime, and Coppersmith algorithm is a method to find small integer zeros of a polynomial. Yeah, so Kornakia works for two variables. So what we did is we needed to guess two variables, for example, x3 and x4, and then to translate the quadratic form to the form of Kornakia. And then in most cases, Kornakia gives you a result, except in some cases where m has too many prime factors. But in this case, you can try to guess another x3 and x4 and do the same. Coppersmith algorithm is perhaps most notably used for RSA attacks, where some part of the key is known. And there are actually quite a lot of versions of Coppersmith algorithm. There's original univariate Coppersmith, and then bivariate Coppersmith, and Coron variant, which works originally on two variables, but it can be extended to three and more difficult to more variables, and Bauer-Roux, which works on three variables. So the idea of these algorithms is that you have the original polynomial, so this quadratic form here, and you want to get, if you, in our case, if you do the guess for two variables, you have a polynomial of two variables, and then you want to obtain another polynomial which has the same zero as this original polynomial, and then you can use the resultants to compute this zero. And in the case of three variables, you need to compute two additional polynomials with the same zero, and again to use the resultants to compute the zero. But the problem is that these polynomials need to be algebraically independent. So just for an illustration of bivariate Coron. So as for Kornakia, you guess two variables in our case, and then you build a lattice. So you see polynomials as vectors. You add the original polynomial, so the quadratic form that we have in the first row, you see it as the first vector, and then you add this original polynomial multiplied by some monomial in the second row as a second vector, and you might add some more polynomials of this form to the lattice. So you are building a lattice, and obviously all these polynomials have the same zero, and you end up building lattice by adding the polynomials of form n multiplied by some monomial, where n needs to be somehow smartly chosen. And obviously these polynomials don't have the same zero as this original polynomial and its shifts, but they have the same zero modulo n. And if you run the LLL algorithm on this lattice, and then if you take the shortest vector that you get by LLL, if some conditions are met, the polynomial that you get doesn't evaluate to zero, at this zero that you are searching for, only modulo n, but also over integers. So you obtain an additional polynomial with the same zero as the original polynomial, and then you use the resultants. Bauer-Roux is similar. The lattice is bit somehow is generated somehow differently, and it works on three variables, and it gives you some more rigor on when these three polynomials that you end up are algebraically independent. And we also tried a bit different approach. So the problem with these Coppersmith algorithms is that they work only up to some point, because they they can find only zeros, only small zeros. So after some point, they don't work anymore. So the idea was with this, which we called hybrid approach, was to split the isogeny into two parts. So we want to find the isogeny between E1 and D2. And we said, okay, let's try to guess the first part, pi1. And this way you reduce the parameters for this second part, and then you apply the strategy that I described here for this pi2, and then you just took the compositum of these two isogenies. And this approach actually turned out to be the most efficient. So it has a better time complexity than meet in the middle algorithms for some range. So for epsilon being between 1/2 and 3/4 for classical computer, while for quantum computer, actually Kornakia turns out to be better. And this is a bit more detailed view on our results. So, so for example, for Coppersmith, the time cost is the same as the meet in the middle attacks. So here we didn't improve the time cost, but still our approach doesn't, it has almost no memory requirements, while meet in the middle attacks, they require exponential memory storage. Yeah, so what about open problems? It would be really nice to completely eliminate the guessing part. And for this, we would need to run Coron or Bauer-Roux on 4 variables, but it just seems very difficult to get 4 polynomials that are algebraically independent. Yeah, and that's the end of my talk. Thank you.
Thank you very much. We have time for 1 or 2 quick questions. Questions for the speaker? Yeah, I would like to ask you, what about the memory requirements for your algorithm? Do you have any to say about it?
It's very little, and it also can be parallelized. Yeah, so it's very efficient in this regard. I don't have exact numbers, but yeah, no real requirements.
Thank you very much. So if you will have more questions for the speaker, let's thank again this speaker and all the speakers in this session. Thank you very much, and we are ready for coffee break.